All right, welcome to my talk. So I'll be going over visualizing data poisoning with networks with my talk today. My name is Maria, and we'll look at the intersection of network science and cybersecurity. In this talk, I wanted to ask, what if we could visualize how training data gets poisoned with networks? As machine learning models become increasingly integral to software applications, they also face increased risk from adversarial attacks, most notably data poisoning. After experimenting with data poisoning, I noticed that training data fed into machine learning models resembled graphical information that could be defined using a visually represented network. My presentation will go further into the concept of data representation and how attacks can modify or poison data within networks. So here's a quick overview of what I wanted to talk about today. I wanted to give some background on both data poisoning and network science before we get further into how we can use network science specifically for threat detection and data poisoning. And then we'll look at two case studies that go further into applications of how we can poison networks. After that, we'll conclude and I'll go into some future work and refinement. So as defined by OWASP, data poisoning is an attack that occurs when an attacker manipulates training data to cause the machine learning model to behave in some undesirable way. Data poisoning occurs by altering data by three methods, so addition, modification, or deletion of data. Interestingly, addition can also mean the injection of data, but as we know, injection does not always mean adding data. So use of injection attacks can also delete or modify. And to demonstrate the addition of data, a privacy-focused colleague once explained to me how he associated his name to the alpaca by changing his names across social networks to those of the alpaca. So my colleague started to post images tagged with his name or username to alpacas rather than his own face or likeness. So for example, he would tag himself in a LinkedIn post with a picture of an alpaca rather than a human. By associating his name or username to alpacas rather than his face, my colleague caused an unexpected outcome of the data, essentially manipulating his likeness. So this story, along with some experimentation with data poisoning, led me to ask the question, how can I visualize the change between untouched data and manipulated data? And that question led me to ask, how can we visualize data poisoning? And how do we do this using network science? So before applying network science to data poisoning, it is important to define some key terms in network science and its significance as a tool. So various systems can be defined by networks, such as the World Wide Web, the nervous system, and even flavor components of food. So this is an example of a graph. This is the web. This is the nervous system. And these are flavor components of food. So all those flavor components kind of share something with each other. So garlic is the big flavor component that goes with a lot of foods. I don't know why starch, which is up there on the top right, I don't know why it's alone, because you'd think that starch is in a lot of foods, but this is just demonstrating the connections between various nodes and edges within the graph. So going back to network science, I'll keep this slide on for a little bit. Every complex system can be defined by a network, and networks can be defined by interactions between its components. So mathematically, graphs are representations of these networks, and graphs consist of objects called edges, or nodes, and edges that connect these nodes. Below, you can kind of see that there's graphs which are vertices connected by edges, and I'll be using vertex, node, and edge and link kind of interchangeably, but there is a difference between what is equivalent in a graph and what is equivalent in a network. So networks are powerful tools for prediction, but are only as accurate and as stable as their data sources. Paths, or a sequence of nodes connected to one another by edges, allow us to make predictions or implications around the underlying data. Analysis of networks also leads us to some interesting statistics, such as edge multiplicity, that is, multiple edges sharing the same node. Edge multiplicity represents the intensity of certain connections within a network, which can be visually shown with thicker lines stretching between nodes. Conversely, sparser lines mean less edges between nodes. So for example, we can represent flight paths as edges on a map with nodes as airports. Well-traveled paths appear to be thicker due to their higher traffic, whereas unpopular routes would result in thinner lines. Also, there's a few more terms that will be useful in the upcoming slides, but don't worry, I will repeat their meanings and terms in the future. So degree is just the number of edges surrounding a node, and also the average degree, which is pretty intuitively the sum of the total node degrees divided by the total number of nodes. High degrees, or large amounts of edges surrounding a node, indicate a centralized and well-structured graph, while low degree networks represent a sparser, lesser connected network. I chose networks as a visualization technique because not only do they have predictive power, but because graphs are simply easy to intuitively digest and look at. So if I look at the flavor component slide again, we can easily tell that garlic shares a lot of flavor components with other prominent ingredients, and we can kind of draw the conclusion that garlic goes with everything, except maybe starch. But regardless, graphs help us intuitively draw conclusions about concepts and networks that we wouldn't necessarily consider at first. So first, to demonstrate the power of prediction, paths and networks can reveal information about the network itself. For example, US military operations gathered intelligence on Saddam Hussein's clandestine terrorist network using paths in a network. As Saddam Hussein relied on family and social institutions for protection, the US military was able to kind of compromise the network by mapping out a captured official's closest associates and progressing their way into the center of the network. So in this case, the nodes would be the individuals in this network, and the edges would represent those connections. The thickness of the lines, again, would refer to the edge multiplicity. Another example of edge multiplicity is this picture of Chinese companies with foreign listings. In this picture, the Chinese companies are planted on the map as nodes. I see the map is a little bit blurry, but you can kind of see the network overall. So this is another example of the power that networks have in prediction and analysis of the environment of these networks. So we can draw an inference that the impact of US cities on Chinese cities and vice versa with the thickness of the lines. So bigger cities such as New York to Beijing have the thickest lines, implying that there are more connections shared between these large hubs. A map like this between the United States and China might kind of change given the recent current events and the tariffs, but this is accurate as to 2022. So to recap, networks help us understand complex systems such as the brain, neural networks, and global financial networks. It's important to reiterate that the power to create predictions using the networks is only as good as the accuracy of the underlying data. If the data is inaccurate, the inaccurate data leads to false predictions and as such could lead to consequential damage. So how many of you remember who this is? This is Tay, a Microsoft chatbot that was released on Twitter in 2016. So Tay was designed to pick up our language and syntax via interactions with real people on Twitter. Long story short, within a few hours of launching, it started repeating vulgar and hateful language. The important thing to note here is the intention of the chatbot. The chatbot was fully intended to be a fun conversational agent, but after training on bad data, it became adversarial, tweeting hateful language, which was the opposite of the original intent. As malicious language was injected into the model, this is an example of a large-scale data poisoning vulnerability. This vulnerability kind of led me to think, what if we could simulate this transformation of good and bad data? via data networks to show how all of the data relates to itself and to its malicious parts. So as a result, I looked into some tools to help me map out malicious networks, which I'll go over in a bit. But networks help us represent important information, as I have shown you with multiple examples. Networks also visualize training data for machine learning. So all of this vital information should be protected, as tampered networks and data can have cascading results. Training data can be obtained through attack vectors. For example, private data sets can be infiltrated through insider threats or sophisticated attacks, and public data sets or repositories are prone to data injection attacks. With public data sets, poison data can proliferate into other models and applications that rely on these public data sets. In order to make poison data easier to detect, I decided to visually compare healthy networks and poison networks using Gephi. So what is Gephi? Gephi is a network visualization and analysis tool used as a desktop application. So to use it, one can upload a spreadsheet, a CSV or XML file with nodes and a corresponding sheet with edges. It is also possible to build your own network by adding nodes and edges manually and customizing its appearance. It is also open source and includes many different algorithms that help visualize different types of information. In addition, it runs network analysis calculations that provide metrics such as degree distribution and modularity. Since you can also run multiple tabs in a single workspace, Gephi provides an easy way to compare healthy and tampered data in the same workspace. So with this tool, I want to dive into 2 case studies that show the difference between healthy and tampered data. So first, I wanted to explore data poisoning within networks. So I borrowed the Les Miserables network created by Donald Knuth. The novel was created by Victor Hugo, by the way, not Donald Knuth. I borrowed the story because the characters in the story have such deep interactions with each other and form relationships with each other, creating a large social network. This is an example of a network that we can potentially poison. In this network, nodes are characters and links represent the co-occurrence between the 2 characters. There are 77 nodes, and in the default network, there are 254 links. So to poison this network, I wrote a network poisoning script that adds or deletes edges between nodes, in this case characters, either creating interactions that would not exist or deleting several significant interactions that would theoretically change the outcome of the story. So before we get into the graphs, why do we care to poison this? Les Miserables is a fictional story, and there is no real harm done when messing with this novel in a graphical interface. So we're not really causing any real harm. The problem occurs when we scale this one trivial story instance to real-life scenarios like Tay's network spreading hateful language. But now we can get started with the graphs. So here is the original network. The thickness of the lines represents characters, and the size of the node represents how many interactions each character has. I see that it's kind of hard to see the edges, but you can imagine that all of the nodes have at least one edge connecting the graph entirely. So it's a little bit bright, but just imagine that there's edges everywhere within all the nodes. So you can see the graph changed a little bit when I poisoned a lot more interactions into the novel. You can see a lot has shifted in this scenario, and I kind of made a fan fiction of Victor Hugo's book. You can kind of see that there's interactions that shouldn't even happen, but I understand it might be kind of hard to see with the brightness all the way up. So here I deleted a bunch of interactions, which might be kind of hard to see, and some characters are left with only one dialogue. I wanted to use this case study as an example of something tangible that can change when an attacker modifies or poisons data in any way. the degree, which again is the number of edges connected to a single node, is less. And as a result, the nodes or characters in this case have limited connectivity. The average degree as a result is also decreased. And so the network is less dense. Characters are more isolated and as a final result are less developed. All right, we can move on from this case study. In another case study, I explored a more technical network, which I explored poisoning nodes in a network of Java JDK package dependencies. This network contains 1,538 nodes, Java packages in this case, and 8,032 edges that indicate dependencies. By adding nodes that we can add packages that do not exist. Adding nodes is simple in this case, but adding connections between the additional nodes and existing nodes is better from an attacker's point of view, since connecting to nodes with more edges makes detection more difficult. My network poisoning script would add a single node to a node with multiple connections before adding nodes that were all attached to the originally injected node in order to create a dependency cluster, which I will visualize in a bit. The script also modified existing nodes with a simple labeling poison by simply modifying the label of the nodes within Gephi. As a result, an attacker could use this modification technique as an opportunity to include dependencies on malicious packages. Again, to reiterate, why do we care? Why do we care about some Java dependencies? After all, isn't Java everyone's least favorite language? Maybe we should poison Java. But seriously, the impact of being able to mess with a web technology related data set is significant. The consequences of data poisoning in Java dependencies is significant. The injection of data could include the injection of malicious data, modifying healthy data to be malicious, or even benign data that could be anything, or the deletion of these dependencies even. But I also wanted to address how is the training data itself affected. Training data can be affected in two ways. One being the training data that is being used to train models specifically for Java dependencies or creating further dependencies, or two, affecting components in public software, GitHub repositories that relies on outsourced training data. Data that is used in these repositories can be linked to poison data, creating a subtle but not so obvious attack vector. Let's get into the graphs. Initially, I did a really small modification that is really difficult to see, and I don't expect you to see. How could we ever see the difference between these two graphs? So I only added 3 nodes in this case. I highlighted them with Gephi, which is impossible to see from here, and I also connected them. So on this slide, here's a closer look. You can kind of see them. So I highlighted them in green to show the attacker's presence. You can kind of see the labels of the various dependencies. So, however, these poison nodes were added in rather than modifying. So what if we modified the edges between the nodes by adding connections that were not supposed to be there? So here I modified this entire already existing cluster of nodes to be green to demonstrate modification, because it's more blue in this case. So the attacker in this case would poison these nodes by altering their data rather than adding or deleting anything. For Java dependency groups specifically, it could be assigning their values to null or just having false lines of code. So here's a close-up. In this case, I labeled these modified nodes with null to demonstrate the poison more clearly. So through my case studies, I want to demonstrate the differences between healthy data and poison data. By visualizing mathematical differences via graphs, we can prove that data has been altered in some way. In addition, we can detect data poisoning by labeling the data that we use, as seen in the Java dependency group example. But how else can we detect data poisoning? We could also detect it through the data itself. Data provenance is the concept of the history of a particular data set. So what has changed from set P, set Q, and set R, and what exactly is the change? You can think of it as a diff function from your favorite programming language, or even when you upload to a GitHub repository the lines of code that changed and the lines of code that remained the same. What I want to illustrate is that we can also track these sort of changes in our databases to use for threat detection. So to quickly recap, we know that private and public datasets can be infiltrated. Whether private or public, datasets can be infiltrated somehow, whether it's through insider threats, sophisticated external attacks, or just regular data injection, which is what I wanted to show here. And I want to most importantly reiterate, our LLM data is trained on private, but more frequently public datasets. For this purpose, data has to be healthy, or it's doomed to take the chatbot's fate. So from friendly conversations to hateful and vulgar language. I've shown you data poisoning, and I've shown you the injection, modification, and deletion of data. So what about possible solutions to this problem? Well, private datasets need to be private. And what I mean by this is access to private datasets must be restricted, ideally with a passkey. These users should abide by the principle of least privilege, and users of these private datasets should only be given the access they need for that particular dataset. And also, I would like to use my script to be used for possible incident handling. So the modification of data should be monitored and tracked and alerted. And through a before and after snapshot, we should be able to see the difference or data provenance of that data. Finally, LLMs need to have guardrails. If you've ever asked ChatGPT or Claude or your favorite LLM a question about cybersecurity, you know that it will tell you certain things, but not others. We can have strategic rules that define what we want AI to train on. The LLM should be intentional, and it should internally check what goes into it as an input and also what it will output. So as part of future work, given data provenance metadata, I'd like to implement visualizing the change between healthy and poison networks similar to diff. I want to believe that this problem can be approached from the offensive and defensive sides of security. So I'd like to be able to truly demonstrate sophisticated attack vectors for datasets. Finally, automating data poisoning detection through network statistics will help make the lengthy process of compiling graphical evidence of data poisoning much easier, as I wouldn't have to go through the process of running a script, generating a graph, and running that graph in Gephi. Although I enjoy the process personally, I'm sure we could all use an automated process that compiles graphical evidence of poisoning for us. So behind every complex system is a network, and behind every network are nodes and edges that define the network mathematically. In order to have accurate and powerful networks of data, we have to protect the data within them from data poisoning attacks. So by visualizing data poisoning, we can more easily detect tampered data and highlight an attacker's presence within a graphical network. Thank you.